you all. Good. We're getting there. We're getting close. I feel it. My skin. Right, yeah, I was in the room just now preparing this. I've been kind of busy over the last couple of weeks. So I figured what I'm going to do is a sort of very, very quick talk about the stuff that I've been talking about for the last 3 months on the tours, because I suspect many of you haven't been, in fact, certain many of you haven't been on the tours, and I figure it's probably kind of helpful so we're on the same page. And then I'm going to talk about the roadmap and the services. Got a little bit of material on that, and then most of it I just want to have a sort of free-form discussion, so you can ask questions and I can at least try and tell you about stuff that you actually want to know about. Good. So I've shown this slide a lot. It's one of Sean's, and it's on the nose. We're on this side, right? Important. So, this slide, if you ever interact with anyone in the crypto industry, or interact with anyone outside of the crypto industry about the crypto industry, then this slide should be in the front of your mind. Yeah? This is how you tell them what it is that we're doing and why it's different to what everyone else is doing. Yeah, except maybe a little bit some people in it, right? So it's like, this is crucial material, yeah? And I mean, this slide was exactly as it was, I don't know, 4 months ago, 5 months ago, the beginning of the year, before the blind signing incident, right? Before the president invited everyone to come and offer loyalty, right? It's like, okay, but we're on this side, right? Crucial, memorize. Now I've described Web3 in a bunch of different ways. Less trust, more truth being one of them. I actually rewrote that for a certain single-party country that I visited recently, because I figured it was probably a little too on the nose. But actually, I'm quite happy with this description. Resilient public digital infrastructure. So again, if you're chatting to people that are maybe not crypto industry people, right, particularly not crypto industry people, and you're trying to explain to them what it is that you're doing, this is what you're doing. Yeah? Building public digital infrastructure, like servers, right? But resilient ones that can stand up to a very chaotic, brave new world. Yeah. Why? Well, this stuff is like kind of all news, really, but it's there. It's real. Yeah. We need resilient stuff, and blockchain. Like people get like caught up on like hashes and Merkle linked lists and blah blah blah. It's a computer, right? That's all people need to know outside of the industry. It's a computer. Building a protocol that manifests itself as a computer. Yeah? Just a magic internet computer. That's all. Magic internet, and in Jan's case, supercomputer. Alright, good. That's the first bit. Second bit, Jan, protocol theory. If you're talking to someone technical, they get a bit deeper. You want to tell them, what is it that Jam does differently to other stuff, right? Well, one of the first things that you need to sort of set up is the idea that there is a sort of trilemma going on, right? As a system grows, it either becomes incoherent, which means bits of the system are not bits of the system change and should change other bits, but those bits haven't changed yet, right? So it's kind of like it's in a sort of indeterminate state. And this is problematic, right? Or it goes slower. because it can also just like proceed more slowly, or it proceeds without sort of having coherence with itself, without a consistent state, or it doesn't grow. That's all, right? But it's one of those, two of those things. One of those things has to give, yeah. And that's the basis of jam. That's why once you realize this, you say, right, well, we want to handle more accounts. We want to handle more data, yeah. We want a bigger system. We want our system to scale. We want to scale it out. But we also don't want it to go really slow. Yeah, we don't want to have to slow everything down for the amount that we scale it up. That would be crazy. That would, then we don't even process that one transaction a second. That'd be no good. So what do we do? Well, something has to give, and what gives is the internal consistency somehow, right? And one of the sort of lessons with Polkadot was, well, you can sort of give that internal consistency on a very persistent basis by basically splitting everything up into different silos, parachains, in Polkadot's case, L2 rollups in Ethereum's case. Or you can do something cleverer, which is what we're doing. And if you want to, like, when you're explaining to them, okay, how is it that we're doing something clever, right? What is it that we're doing that's clever? Well, this is, in your mind, when you're explaining, you can't, unless you've got pen and paper, maybe you can draw it out, but like in your mind, this is like a good model to have, right? This is just all of the things that we want to be processing on the world, on the magic internet computer, right? Lots and lots of different things, all being processed all at once, yeah? And kind of all in the same space, so they can kind of do stuff with each other, yeah? And then the first sort of magic internet computer, that was what it achieved, right? Which is not a particularly good version. I mean, it's the first one, so it's had a good stab at it, but it's not a particularly good version of it, right? The lines are not many lines, and when one stops, the one starts only when one stops, and there's a big lot of space there because it spends most of its time doing nothing. But it's a start. And then, instead of drawing multiple lines, we can just draw one line because it can only do one thing at once. And then there's some people that have come along, like Solana, that have, optimized it all, made the lines bigger and longer and thicker, but it's still just one line. Yeah, it's not distributed across the network. And then others have come along and said, let's just have lots of them, but that's really insecure. And then Polkadot comes along and says, let's have lots of them, but under the same sort of system, but each one is siloed. Yeah, that's how Polkadot went and sort of broke this trilemma, right? It said, we want to scale and we want to go fast, so what we'll do is make it a bit incoherent, and that's how these lines denote how it's incoherent. Yeah? These things can't affect each other except by sending messages that take a little while to arrive. The messages can't be very big or all the rest of it. Okay, so how do we explain jam? Well, we break the coherency, but we do it in a cleverer way. Yeah. So jam is big and it goes fast, but it turns out that it has this sort of coprocessor or set of coprocessors. Yeah. Kind of like a regular computer has GPU coprocessor that kind of does particular kinds of computations very quickly, but using its own kind of memory and kind of set aside from the CPU. You kind of send work off and it does work really fast, and then gives you the results sometime later. Yeah, you're not going to do stuff that needs to be a lot of toing and froing with CPU memory or CPU processing on the GPU. Will go really slow because there'll be this sort of gap that you have to cross very often to make it consistent with itself, essentially. So this is sort of where you've got to kind of study this diagram a bit to really understand what it is that we're doing with jam. But I think once you understand it, it should be you should be able to explain. You should be able to explain what it is that Jam does differently to Polkadot, and why and how it is that Jam's breaking this size, speed, synchrony trilemma in an interesting and effective new way. All right, good. Now, next thing, Jam terminology. There have been some changes in the terminology. There might be one or two more before the grey paper hits 1.0. The one I'm not very happy about at the moment still is this in court on chain thing, because this has confused some Ethereum folks that think, oh, if it's not on chain, it's not secure. So this might be changed, I don't know, something like asynchronous and synchronous or something. I'm not sure. I haven't come up with it. If you have any good ideas, then let me know. Maybe we'll discuss that afterwards. Good. I think you probably should know this. So one of the changes that I made is tokens. So there's a concept now of an authorization token. This is just an opaque bit of data. It used to be like I don't know what it was called actually, but it's basically the inputs into the is authorized function. It's now called a token, an authorization token. And then we have a concept of a digest, which is the sort of bit of data that sits between refinement and accumulate. So refinement for a particular work item outputs a digest, and that makes its way into accumulate. It's kind of like a digest of that work. So I did this work, and here is the sort of a little bit of data that I'm using to describe the implications of that work. Good, I think this shouldn't be too foreign to any of you. A bit symbolic, but you should sort of be able to sort of figure out what it means. Okay, so yeah, packages include a token. That's the thing that we sent into the authorizer. Authorizer in Panex if it's invalid. And then the authorizer gives some trace. That's a new term, right? Trace just means the authorization output, or the authorizer's output, yeah? That's what I've called it in the past. But it's a bit of a mouthful and it takes a long time to type, so it's like, we just call it a trace. It's a trace from the authorizer. It just basically tells the rest of the pipeline why the authorizer might actually authorize this work package to be done. And it might be, for example, that some account said that, signed something and they, that's they're a collator, right? But whatever, it describes why. Be aware, trace. And that's something that I've moved into the grey paper, I think, as of 065. So if you'll notice this terminology if you've been keeping up to date with the grey papers, grey paper releases. Authorizer pool and queue, that's not changed. Authorizers arbitrary code, that's not changed. Is there anything else? No, I think that was it. Yeah. So 48 kilobytes of digest new term. Accumulate gets the digest and the traces. Good. All right. Fine. Core VM. Probably a few of you have seen some of the Core VM stuff, what we've been doing, particularly the Doom demo. Why bother with Core VM? Well, because it's really a pain in the ass to develop on blockchain. So let's make it not a pain in the ass. And what does Core VM give us? Well, this is the ideal. Right? This is the ideal situation that we would like to have. This is Jam, which doesn't provide that, obviously, it's some mad architecture. But Core VM uses Jam to give you this, right? Which is pretty cool, right? Getting closer. Now, if we look at it, what's the main thing? Well, the big arrows from top to bottom, that's good, right? That means that there isn't a break in execution every block, yeah? It just apparently just keeps going. Now there's still lines between these processes, if you like, these execution threads. So they can't directly talk to each other, like they're not sort of sharing memory or whatever, but they can send messages. That's the idea of core VM. It's halfway to core play. Docker for Jam. Right? Can run normal software. Okay. What's happening in the future for core VM? So at the moment, you saw with the Doom demo, there's a concept of like video output. So you can run an executable inside of core VM on chain, and you get you can have like a window that is checking the video output from this core VM instance. The core VM is basically just a computer, right? It really is. It's got a, in our case, it's got like a graphics driver, right? What does the graphics driver do? Well, it shunts data into the data lake and puts a little pointer to it in the state of the service, and then something else can watch the state of the service, pull the data out of the data lake, and display it in a window or in a browser or whatever it is. But that's just one example of a virtual driver for the core VM computer, right? There can be many other virtual drivers, right? Many other kind of virtual devices, right? Audio output is an obvious one. Yeah. So we can actually start having audio stream as well as a video stream, and it will appear to core VM basically as an audio card, right? Terminal output. So you can actually just push stuff out onto a virtual terminal that can then be monitored in the same way as monitoring the video. Keyboard input, like in principle, we can then send transactions or send data. I mean, they're not really transactions. They could be transactions, could be signed data, but send data in some way into core VM and tell it this is keyboard input data. Fixed storage, like ROMs, basically. Right? And we can imagine using the pre-image lookup system for ROMs. LAN, right? So you can, like core VM instances can send messages to each other. And maybe even things like cartridges or something, like kind of basically replaceable ROMs, and this could be done through extrinsics. So you can actually not just have keyboard input with extrinsics, but you can just have like large amounts of data coming in through extrinsics. So that's the future sort of roadmap for core VM. Core Play, which is sort of the branching off from core VM, is basically just core VM but with co-sequencing. Right? So you might be familiar, if you're familiar with some of the Ethereum ecosystems. Currents, you might have heard of co-sequencing. I want to talk like a little bit about like why don't we just have like many different kind of smart contract environments and let them send messages between each other? Well, basically it's very limiting, right? It's not ideal. Really, we want just like a really big environment, and it's just easy for everything to interact with everything else. That's what we would like, right? Coherency, at least apparent coherency, even if it's not actual coherency. So again, that's the ideal. So core play delivers this. So what's this? Well, ignore the colour blocks, that's not so important. But the basically, we still have the lines that are splitting up our execution processes, but the lines are dynamic. They're moving around. They're adaptive. And essentially, we can pair or tuple up our execution processes on time windows, so that they can, the ones that want to interact with each other, the ones that have economic value for direct interaction can do, and the ones that don't. Obviously, we are limited because of the size, speed, synchrony trilemma. We can't just remove all of the lines and have them all execute in the same space, or something would have to give. But because we can move these lines around, we can break not break the trilemma, we can apparently break the trilemma by providing synchrony or coherence only where it's actually needed. but changing where it's actually needed on a potentially block-by-block basis probably wouldn't be block-by-block, because that would be a very difficult optimization problem to solve in real time in a decentralized setting, but maybe several blocks later. And yeah, as I say, this is basically co-sequencing or co-scheduling, but with actors or smart contracts, actors really, instead of blockchains. The nice thing is you can add more cores to core play, and you just can execute more actors. Right? You just kind of execute more actors. It's kind of pretty scalable. Now you can't execute more actors in a single core, of course. So you're not going to be able to, bring these bring this sort of group, make these coloured rectangles wider. Doesn't work like that, but you can have just more actors executing all at the same time. And you get apparent coherence, apparent global atomicity, apparent no fragmentation. Yeah, it's a bit of smoke and mirrors, but it's smoke and mirrors backed by good theory. And how do we do it? Well, we basically keep our state atoms small. We work on actors, not blockchains. That's what it comes down to. And then because we keep our state atoms small, we can do regular repartitioning, and we have like a very effective platform for doing this. Like Jam is designed for core. This is sort of the key thing beyond protocol compatibility that we wanted to achieve. If anyone asks you why not zero knowledge proofs, basically because they are 2 million times more expensive than ours. Right? And they might say, well, we've got VC funding, and we can totally subsidize all of our ZK server costs. All right. For how long? Yeah. When you get 100k TPS, then how long? How long can your VCs fund this totally unsustainable economic growth? For what it's worth, also, the cost that that ZK would introduce is not merely economic; it's also environmental, right? If we re-implemented Jam with ZK and just footed the bill for GPU supercomputers to produce proofs really, really quickly, I suspect. I don't know for certain, but I suspect there's an argument it could actually be possible. It wouldn't be economically viable, and it wouldn't be environmentally sustainable. Like, we'd be kind of using crazy amounts of energy. 2 million times, roughly, more energy than Jam is using. Yeah, and I mean, Jam's pretty efficient for energy. It's uses elves, and if you look at the graphs, elves is pretty efficient compared to stuff like Solana and whatnot. But still, multiply elves by 2 million, and it's gonna eat up a lot of electricity, right? It's gonna burn through a lot of fuel, and that's just not sensible. That's just not a good thing to be doing for the world. Yeah, and I mean, this doesn't seem to bother the Ethereum folks much, but it would bother me. Like, if you've got something that burns 2 million times less coal, I would use that, even if the alternative that does burn 2 million times more coal happens to be more mathematically beautiful, right? Sorry, but there's a point where mathematical beauty doesn't fucking matter. Okay, good. Roadmap. Now, I've linked these because I want to go over this stuff with the GitHub. So let's open the links. So I'm going to go over each of the 4 things that we have to do to get to 0.7. First thing is this placeholder for refinement entropy. So your 0.66 brought about this accumulation entropy, right? Which there's a small on-chain entropy that the chain uses for doing, I think, Safrole is the main purpose for the on-chain entropy. Eta this funny N with an extra sort of tail. That's all very well, but if you want to design a service, as we keep sort of banging on about, service logic should be primarily in refinement. You should be only doing the stuff that actually has to be totally coherent in accumulation. And refinement doesn't have access to the on-chain state because it's stateless. So how would refinement get, refinement, you can oracleize in the anchor box at a 0, but by then it's going to be really old and everyone's going to know it. So it's not very helpful. Well, refinement could have its own entropy. This is what this sort of came to me a few days ago, which is relatively new. Basically, our guarantors have keys, and they are going to be signing the work package. So if they're signing the work package anyway, why not sign it with a VRF proof and feed in some deterministic randomness that wouldn't be known up until the point that the guarantor is actually guaranteeing the work package. This allows us to have some pretty high quality entropy inside of refinement. So very high bandwidth, very high throughput, high quality entropy. There's a little bit of, we don't have full consensus between the 3 guarantors that are going to be guaranteeing any particular work package. So we have a slight issue. One of the things that we might possibly do is use some exotic crypto, so that we only need 2 of the 3 guarantors to do to create a deterministic VRF between them. It's kind of threshold VRF thing. I'm not sure if this is viable at the moment because I think last I checked you need a trusted setup for basically an N of M VRF. If that's not possible, then we can just either say, basically allow the work package to choose whether it wants all 3 or one particular guarantor to sign or to create the VRF output, and because of refinement entropy. If you have all 3, then it's totally secure. It's a security indeed, right? Unless, the only options that the guarantors have are basically stall the core and lose their guarantor money, or put their VRF output in and give you your deterministic entropy. But there's either way, you're not going to get anything biased, right? You're either going to stall or get unbiased entropy. So that's if you want high quality entropy. If you're a work package producer, you want high quality entropy, you would do that. If you don't care about high quality entropy, then you could also just say, well, I only want 2 guarantors, right? And presumably the 2 that sign the work package are going to be online, and therefore, or sign the work report, are going to be online, and therefore they will be able to give entropy. So that should work basically all the time. But you might be at risk if the guarantors are malicious, then they could choose between them which 2 give you the entropy, and then you could get one of 3 possible entropes, and it could be biased. So it's kind of up to you whether you want to risk stalling but get unbiased entropy, or not stall but get potentially biased entropy. Most of the time it'll be fine, but in theory. Good, that's the first thing. For 06 series, this is just going to be a placeholder because it will need some cunning networking that will take some time to figure out. So for now, refinement entropy is just going to be all 0s, but we'll put the relevant fields into the work bundle, the work report, the work package, so that when we do come to do it, we won't need to change any data structures, so it'll just be some extra networking. Good. Next one. Support read-only memory in inner VMs. So this has been a long while coming, but this is essentially the ability to recognize when we kick off a new inner VM inside of refinement when it has altered its memory. So to be able to read its memory, and then if it actually mutates its memory on a particular page of memory, there will be some mechanism for us to actually know that. The current assumption is that we will be able to create memory pages that are read-only, as opposed to memory pages that are read-write, and then either protect or sort of unprotect a page. I mean, at the moment, the assumption is that they'll always read write until we protect them, and then they become read only, which is probably the wrong way of doing it. Probably want to make them read only, and then let the program run, and then if it tries to mutate a read only page, we get a fault, and then we can unprotect it and note that it's actually changed. Yes, this will allow us to do important stuff for core VM, in particular when core VM is changing its memory. We want to know so that we know we have to feed that into the accumulation logic and tell it that the memory page has changed given the new hash. And also stick it in the data lake. That's another change in terminology, by the way. It was called audits DA and segments DA. Now it's audits DA and the data lake. Good. Next one, audit the numeric encoding. Now this is something that, Sim asked about quite a lot. It's like, oh, is it variable, is it fixed? Yeah, so I introduced the statistics compilation for like cores and services. It's potentially quite a lot of data, and it's data that's going via the work report. And work reports, it's really tight, right? We only have like 48K, or we're going to run out of bandwidth on the networking side when we are collecting these things together and distributing new blocks. So it's important to be quite well size optimized in work reports. So I chose to make this new statistics data, sort of as compressed as possible with its encoding, which changed how, it was unprecedented largely, right? There were, I think almost all numbers up until then were fixed length encoding. So before 07, I'm going to go through the whole thing and try to change the encodings such that we actually follow some rules for when things are encoded variably and when things like compactly, and when things are encoded fixed length. Basically, if we expect to always interpret a bunch of numbers as a whole, like interpret, mutate, and so forth, then we can use a variable length encoding. If we don't, if we expect to be able to want to prove or mutate or copy or interpret a bunch of numbers individually, like individual numbers within a bunch, then we probably want to use fixed length so that we can window in for that one number, just pick that one number out. And we know what we would know where it is based on its schema. Also, large sequences, if we're talking like 1,000 plus elements, my assumption for now is unless there's a good reason not, unless it's like really key sort of bandwidth saving requirements, then we really need to probably move to a fixed length, just so that disk reading into memory becomes a very simple sort of mem copy rather than having to go through each number of them, 1,000 numbers, and like figure out exactly how big it is. Then host calls for PVM, stick to fixed length for window reads. Like host calls for PVM, the expectation is that the amount of memory addressable is going to be very important. Right now? And therefore, the less memory we can make PVM execution need, the better. It's worth saving. Worth saving those bytes. For example, inside of refinement, you've got this, you've got the work package, right? You're sort of pulling in a potentially 5 megabyte work package. Well, 5 megabytes is quite a lot of memory. I mean, it's not a lot of memory for this laptop, but it's a lot of memory for potentially, PVM consensus execution environment. And it might be that you only want like a 32-bit value inside of this 5 megabytes. So it kind of makes sense to be able to do a windowed read. Just pick out 32 megabyte value, move it into memory rather than take the whole 5 megabytes, move that into memory, and then just copy out 32-bit. But you can't do that if you're using variable length encoding. You need to know where in the 5 megabytes this integer is. Now, that for work packages, that's a bit of a, there's a lot of variable length stuff going on in work packages, but in, and that's something that we'll come to in the 07 series, but for smaller data structures, it does make some sense to keep things variable length. Good, yeah, and then also for just I/O into PVM, there's another reason to keep it fixed length, which is just optimizing encoding and decoding within PVM. Again, trying to save guys. Okay, good. So that's something that will happen probably the last thing that I'll do in the 06 series, and then finally the last item on the list. Yes. Introduce the accumulation outputs into state, and those are all the Merkle mountain belts. So the moment we're storing quite old Merkle mountain belts, we're storing the Merkle mountain belt, if you remember, in the recent blocks beta state item, and we're storing it up to, I don't know, 8 blocks in, right? And the thing is we don't need we don't need any old Merkle mountain belts. We only need one Merkle mountain belt from the last block, because that's the only thing that we ever read and change. So we should get rid of that, but we should also store the accumulation outputs of the most recent block. Why? Because it's a pain in the ass to get them otherwise. So, Merkle mountain belt, if you remember, the point of having a Merkle mountain belt is so that we have a Merkle, a sort of ever-growing Merkle data structure, with each item being a Merkle tree that encodes each of the outputs from the services that were accumulated. Yeah? So that basically, if you've got like, I don't know, a service that wants to send something into Ethereum or something, then you can denote that in the service, somehow introduce that commitment to that inside of the services, inside of the hash of that service's accumulation that did the transfer or whatever, and then prove that in Ethereum really easily, right? By digging into this Merkle mountain belt, which presumably an Ethereum lifeline for Jan inside of Ethereum will be able to give you the root of, and then take that Merkle mountain belt leaf value and dig deeper into that to find your services accumulation output commitment. And there's some part of that tree, and then you can prove it from your services accumulation output commitment, which presumably you're somehow tracking separately, as because you are the builder of these services work packages. But getting at where it sort of fits into the Merkle mountain belt's easy enough because you're tracking that with the blocks. But getting where the Merkle mountain belt commitment fits, or where the service accumulation commitment fits into the Merkle mountain belt commitment, is a bit of a pain. There's no way of doing that. You'll probably have to have a modified client at the moment to be able to see what other services put stuff in that Merkle mountain belt commitment, so that you can then pick apart it and make a proof for your services commitment inside of it. So let's just make everyone's lives a bit easier, and instead of hiding this data as part of the sort of state transition algorithm, actually just stick it inside of the state. Yeah. So probably one of the next changes, this is probably the next one I'll do, and it will be just to have an additional state item that tracks that stores the last block's the commitments from the services, from the service accumulation, that it's going to be Merkleized into the thing that gets stuck in the Merkle mountain belt. Yeah. So it becomes very easy then to get a proof for any particular services commitment into a Merkle mountain belt leaf. Good. All right. 06 roadmap looks like, and I'm hoping to get that finished by the end of the month, right? So 07, 0, I'm hoping will be in the next 3 weeks or so, hopefully soon. Right, what's next? So 07 series. Now, if you go to the roadmap, let's see if I can do this. Milestones.
It's in the issues.
So there's quite a lot of stuff in here, and to be honest with you, I think not much of it's going to make it in before 1.0. One thing that I think will is exposing entropy into refinement, so that's one thing that we'll probably do in 07. So we put the placeholder there in 06, but as I said, this should be basically just networking. So essentially telling the guarantors what to do, when to do it. And there is already a pretty clear roadmap. This I've yet to go over with Al at the foundation, but I think he thinks it's a reasonable idea, so it should be good to go. What's next? Basic versioning for account structure. This is probably something that will go in. May even move that to 06. It shouldn't be too much. It's basically just going to be sticking an integer at the beginning of the service structure. Sorry. Yes, the service structure. What next? Gas pricing is slated for 07. That's not my department. And that's it. So there's a lot of stuff in here, but as I said, I think these are all interesting things to consider, but I'm now at the point where I think we should just push to 1.0. I think we have something that is viable. So what? Let's have a look at these things that we might consider. I don't know how many of you have already gone through this list, but I'll take you through it. So heap style encoding. What's that? Basically, it's an encoding, a serialization mechanism that keeps all the fixed length things up front and minimizes the number of things that we have to sort of read in order to work out where a variable length thing is. Right? So Ethereum has something a bit like this in its simple serialization format. But I don't think it does it particularly. It's a good idea, but I don't think it does it particularly well. I think probably because it's more about Merkleization that they want to optimize for, rather than a sort of combination of windowed reads and size, which is more what we were trying to optimize for. But still, the general direction may be interesting. It's got some. The main issue with it is that it blows up the size of it, right? Because you're putting all the fixed length stuff first. You have to put something in for the variable length thing, which is basically where it is that you're going to be able to find the variable length thing. So you kind of put a pointer in instead of the thing itself, and then the pointer is fixed length. And if it's like a variable length list, then you put like both the pointer in and the size of the list. But both of those need to be fixed length. So, with the pointer and the size, of course, you can do range checks, and you can work out where any particular item is in the list. If it's fixed length items, if it's variable length items, then you can work out where the pointer is that will tell you where the variable length item is. Yeah. But as I say, this essentially blows everything up in terms of size. So we have to go through the data structures and work out if the size increase is worth paying for the ability to basically do windowed reads into the structure. I'm not sure if it is. Yes, combining accumulate with on transfer. This is an interesting one. So, you know, this used to be sort of not really possible because we only had one accumulation round. So we would either have to store the old transfer, the deferred transfers on chain until the next block, which, you know, there could be a lot of them, and then you've got like the problem of like state IO. Or we would have to introduce a sort of second accumulation round, and then potentially a third or a fourth and a fifth, depending on if those accumulation rounds transfer things. This changed quite a bit when we introduced queuing into accumulation. Yeah, by introducing queuing into accumulation, we're now able to defer accumulations to the next block, or indeed indefinitely into the future, and have multiple rounds of accumulation in the same block. In principle, then, we can probably need to get rid of the on-transfer entry point and just say it just accumulates, but it accumulates without a work item. We just have two types of accumulation, or two types of accumulation input per service. We have work item accumulation, or digest, I should say, accumulation, and we have memo or transfer accumulation. Yeah. It's right on the cusp, because it's a fairly significant change, particularly to the grey paper, but it is quite a nice simplification. So I think this is just going to come down to how much time there is within the 07 series. Good. Okay. Right. Basic versioning for account structure and service code. This will probably get done anyway. Reserving some cores for processing in the queue. I mean, yeah, not clear if this is going to be particularly helpful. I think for this we just have to see how real services work. And it may be that it's like, yeah, it could be interesting, it could be useful, but you just don't really know until you've seen it, real services in action, and by that time maybe you're already on the way to 1.0. Okay, this is almost certainly not going to happen before 1.0, but removing the pre-image lookup stuff in favor of DA lookup. Why not? Well, the whole point of pre-image lookup is that every node stores this data, right? Which means it's data that is always known to be available on all refinement nodes, on all guarantors, on all auditors. Yeah. If we put it in the DA instead, then it's not available, and there's a cost associated with getting it, and then we have to introduce that cost into pre-image lookup, which is an issue. So I can't. The only way that this could really work is if we introduced a sort of special DA entry that didn't split it up and send it around the network, but instead had every node store the data directly. That would be one way of doing this. But then if every node storing the data anyway, does it really matter if it's storing it inside of the DA versus storing it on the chain? I mean, databases should really be, for pre-images, storing it in a separate part of the database as just a hash lookup anyway. So I don't see it happening. But it's something to think about. Okay. Right. Passing the core index into refine. So we don't currently pass the core index into the refine function call, right? Into the refine code. Why not? Well, should it matter? It shouldn't really matter which core your refine code is executing on. Like, maybe it's going to do like funky or unexpected stuff if it has access to this information. Maybe. But maybe it's helpful. I don't know. Something to consider. It's a pretty trivial change. If you have any thoughts, feel free to voice them. Next, a facility for tracking integration. So integration, if you're not familiar with this concept, is the idea that accumulation may fail for any particular conceptual repercussion or implication of refinement, which is itself a repercussion or implication of the work language, right? So the pipeline work package gets introduced, it gets refined, you get a digest, it gets accumulated, it goes into state. But if it fails at some point in this pipeline, and you can't be, as an external onlooker, if all you know is that the work package was introduced, then you can't be, it could fail, and therefore you can't be sure that the implications of that work package are going to be reflected ultimately in the state of the system. Yeah? It could drop out at some point. It could drop out because refinement failed. Maybe it ran out of gas, maybe there was just an incorrect configuration, it put other work items in that had too many exports, and then your work items didn't have enough exports, whatever. It can fail for a bunch of reasons, you can read about them in the grey book. Accumulation can also fail, right? It can also kind of run out of gas inadvertently. For very, very trivial accumulations, you can probably code something that is infallible. But we're not going to be dealing with trivial accumulations. We're probably going to be dealing with quite complex accumulations. At which point we need a way of checking to see if a particular sort of work package or work item has actually sort of integrated its implications into the machine, into state. How would we do this? Well, one obvious one is that we'd send a memo to some other service that cares, right? If we imagine we have two entangled services, maybe they're doing an atomic swap, right? A currency swap. And you have one service wants to integrate the repercussions of the currency swap, but it obviously doesn't want to do that until it's certain that the other service is going to integrate its side of the repercussions of the currency swap. Yeah? If one side integrates the repercussions of the currency swap, the other one doesn't, it basically means someone's making money, right? Someone's screwing the other. Yeah? It's like an atomic action. It must be enforced as an atomic action. And it's one of the things that's important to understand when designing services, merely because two work items happen to be in the same work package, or indeed one work package happens to be a dependency of another work package, does not mean that the implications of those work items will be integrated into the service's state. Things can go wrong before that. So the idea for this is to have a specific facility for tracking integration. So that basically two services that maybe have a work item each in a work package can say these work items are entangled. Do not integrate one without the other. And then you can have some hooks inside of the accumulator that basically says, well, this is what I kind of want to do, but I only want to do it if all entangled work items also do it. And we have some abstraction for that. My feeling at the moment is that abstraction might be over-engineering, and we really need to create some services that do entangled interactions with each other, and see just how difficult it is just to use transfers and memos and so on. My gut feeling is that it will probably be fine without a specific, a particular abstraction facility for it built into the protocol. We'll probably do it at the service level. Something to consider. Next thing, PVM host calls. Two PVM host calls that we're thinking about. Mem copy and mem set.
Well, this would be probably instructions, but I have already prototyped the mem set. It works relatively well, but there's still some corner cases to consider before we can merge it into gray paper. But I've been holding off on this a little bit, because this might be increasingly important when it comes to interactions with the gas pricing. Right? Because for gas pricing, memory access instructions might be relatively expensive. So these two extra memset and memcopy might be a way to alleviate some of those costs too. So yeah. But all in all, this should be these two instructions won't be like a massive change. Just two new entries to the instruction list. So whenever we want to have them, it should be simple.
Cool. in any case, slated for the 07. As I said, most of 07 is probably going to be pushed back, but this may very well be one that we need. What else have we got? Right, two very interesting ones. First one I called Slipstream. This is this is the idea of having run-on packages. So if you've ever played Guitar Hero, you probably have the idea of this like hammer-on thing, where you kind of start one thing and then you can kind of move your finger around and play more notes without actually strumming anymore. It's a little bit like that. So you have one work package that sort of kicks things off, but then you have later work packages that are kind of dependent on that work package being before them, but only, but sort of don't, they're not kind of full work packages. They assume that you've already got the state, some transient state from the previous work package. In essence, the idea is to reduce the latency, right? So with this, what we would do is, this would be combined with having much smaller block times, like 1 second block times. Now, if we have 1 second block times, it's like there's, kind of too much. Well, actually, the biggest problem with having 1 second block times is that we don't have the state around from the previous work package for the next work package. We have to put that state into the DA and read it back out again, because it might be on a different guarantor or auditor. Yeah. Basically, whoever's going to be refining this thing, it might be a different person to the block before. So we have to go via the DA, and going via the DA is slow compared to just having it right there in memory, which is what we have if it's executing on literally the same hardware. So if we move the block time from 6 seconds to 1 second, we're going to basically have an awful lot less that we can do over any given 6 second period. Yeah. Because when it's 6 second block times, we can basically save we have all of our working state from the previous 5 seconds of that final 6 seconds. If it's 1 second block times, then at that final 6 seconds we have no previous state. We have to fetch everything. So the idea is basically to say, well, we have 1 second block times, but we're going to split things up into 6 second sort of chunks of time, and make sure that the 6 second chunks of time, they're always at the same auditor and guarantor. Guarantor's relatively easy because we already have a particular guarantors stick around over large periods of blocks, like 10 blocks at the moment, before they get rotated. And they're still the same, like 10 blocks before they get rotated. Auditors don't. Auditors audit work packages individually. And this is the problem. So we kind of basically say, well, for auditing, we're going to store all these 6 work bundles together. And when they get audited as all 6 of them, not as just one. And this could allow for the possibility of having much lower latency blocks, like much smaller blocks, going through the pipeline and having implications placed in the service state, even before that 6 second period is finished. If we take it down to the wire, we can probably get it in with like 2 to 3 seconds of latency. Which could be interesting. There's still some issues with it, which is why I don't think it's going to be done before, which is mainly service I/O. Because of course it's not just DA that we have to go to and from in that 1 second. We can sort of manage that by basically saying, instead of going to and from DA, there's just going to be a sort of local state. We may not even reset the VM. We can just keep the PVM memory between the work packages, right? That's a way of doing it. But we still have the digest, right? So we have 48K of digest for 6 seconds, 8K of digest per second. Well, if we if we use that digest to kind of store or commit to the end of our previous 1 second's work, we're going to be using up some of this 48k that we wouldn't otherwise have needed to use if it were coalesced until those 6 seconds. We're kind of storing our intermediate states or commitments to our intermediate states. That will use up some of the bandwidth into accumulate. And that's the main issue that I see with it at the moment. But it might be something that's worth paying. Because with that, if we can soak that up, then we can have like potentially down to 6x lower latency. So something to think about, something to consider.
How do you make sure that these random packages are actually random? Guarantor might just ignore them and just say, yeah, I have just one.
They could, but then we can maybe backload the guarantor payment. So if they don't run the later packages, they don't get paid as much.
But they could have not seen them.
It's true. So it could be that someone just doesn't give them the later 1 second packages. I mean, that's a bit harsh. But we would presume if someone is, on the core, they probably want to use the core. I don't know. Yeah, there's not really I can't see an easy solution for that, but other than putting it in the guarantor's interest to actually include the later work packages, and assuming that if someone is paying for a core, they want to use more than the first 1 second, more than the 6 second. Okay, next. Yeah, final one, self-hosted parameters. This IML, I'm pretty sure, is not going to make it into before 1.0. So Jam has a bunch of constants, right? That big table at the back, list at the back. And now we also have this idea of like chain parameters. That if you're implementing the RPC, you'll be giving back, so you can use Jam top. Why not have the parameters stored in state and then allow us to upgrade or change the parameters in real time? Yeah, I mean, it's kind of nice, I suppose, but one of the things that we get by having relatively fixed parameters is some simplicity in the protocol. Like if you always know the validator, the number of validators is going to be the same, or the number of cores is going to be the same, then parts of the protocol definition quite a lot easier. If they change, particularly, if they change block by block, it's a mess. If they change epoch by epoch, it could be doable. You still got some question marks, like for example, if you change the validators, the number of validators, but your, whatever it is, iota, the next set of validators that you should be putting in, is a different length, how does that work? We could probably come up with some sensible way of handling that, but yeah, it's an interesting thing to think about. I'm not sure of the utility of it yet. I think maybe it doesn't matter that much. We are planning on some upgrades, I think. Like I think at Jam 2, like we have lots of sort of paths that could go down for an upgrade of Jam. But I see it more of a sort of long-term, 18-monthly cycle thing rather than something that we want to change once every week or two. And then this seems like possibly quite a lot of work for something that we're not going to change very often. Good, and that concludes the 07 series. So yeah, as you can tell, there's a lot of things to think about, but most of them I think are probably not worth the effort and pushing the timeline back at this point. Alright, so what is the timeline? I want to get 07 done this month. There's not much to go. Getting pretty close. 08 and 09 in June and July. And we're only going to achieve that basically by not doing any of these things that I put under consideration, which I think is fine. I think the utility is, for most of them, is just not proven. The only one, as I said, I'm really tempted with is the on-transfer accumulating amalgamation. 09 is when the paper gets audited, and I want that to begin in July. And then M1, this depends a little bit on Davide, but M1, I would acceptance. We can start, or we can start accepting M1 candidates in June. And then hopefully M2, the M2 conformance suite is going to be quite a lot more work than the M1 conformance suite, but obviously ASAP after then. And given that there'll be so few protocol changes between 07 and 09, that'll center mostly around the PVM, so the extra PVM instructions, the PVM gas. Then hopefully that will free up a bit more sort of bandwidth to really push on the conformance tests rather than push on sort of constant catch-up to the great paper spec. Good. Yeah, so post 1.0, I've said that top paragraph, I'll say it again. If it's not clearly useful, it's going to get postponed. So after 1.0. 2.0, uncertain at this stage, but my feeling is that 12 to 18 month upgrade cycle seems reasonable, and obviously we can't make it too little, otherwise they'll just be constantly hard forking, constant grind, that's no good. But I think maybe, year, 18 months, hard forks, not too bad. But we'll see. Maybe actually we don't need to do, maybe we go through all of the potential changes and actually none of them are going to be that much useful. Okay, moving on. Services. Other than core play and core VM, which I already covered. Well, some stuff I'd like to see, not necessarily from parity, is these, right? Let's start trying to code up some services, right? Now we've kind of got the protocol more or less sorted. This is when the fun stuff starts. Right? So let's make a simple token service. Like, I mean, really simple. Like, it doesn't matter how dumb and inefficient it is. Let's start coding it out. So one example of like a very simple tokens thing would just be, you just use the entire core to do a single transfer. You just create a new service, one service per account. The account has like a public key associated with it that the authorization checks, and the auth token is just, so the auth trace is the public key whose signature checked out. You buy a core with your key. In the core, you say, I want this key to be able to do the transfer, or rather buy core time to be able to do the transfer. And then you goes through refinement. It's trivial. It just passes the auth trace into accumulation. The accumulation checks to make sure that the public key matches, the authorized public key matches the services associated public key, and then if it does, it sends the tokens. Very, very simple, shouldn't be very much code. And I think this is the sort of thing that we want to start messing around with. Very simple staking, so just let's see if we can make a staking service. Right? Have a think about that. Shouldn't be too hard. Obviously, we're going to need to be able to transfer tokens. into a service. And we're going to want some way of like figuring out the validators given the tokens. Something I put down here, very simple core time service, buying core time or allocating core time. Very simple bridge. It'd be nice to be able to bridge it into Polkadot and back again. That's probably not going to be very simple. Very simple voting. So basically just a way of like upgrading the staking and the core time services through some, I don't know, stake weighted vote system probably. Sudo. I mean, I guess to some extent the Bootstrap service is Sudo, but will probably be something a little bit more sophisticated. Something I would like to see is NPOS state. Try and take the code that we've already written for nominated proof of stake and just turn it into a service, or perhaps a core VM executor. Could be a bit easier if it's a core VM executor.
Last year you said you couldn't imagine more than 10 services being built on top of Gem.
There's only 6.
Yeah, but obviously your thinking has changed a bit. Would you build services or on top of services?
I mean, I don't know. This is like silly, this is kind of silly stuff that's meant to sort of get people, you know, meant to help us all understand how to code on this new thing that we're building. Because we don't know how to code on this new thing. Like, we've never coded on an architecture like this before. So it's more just sort of.
And the tooling is also very raw. We don't have tooling to build.
We have Cargo. It's pretty solid tool. I mean, the APIs. Yeah, we don't have much. Not too much tooling, I guess. We have some stuff. We have the Jam CLI thing that I coded at the top. We have a bit of API stuff. I think it's too much. And I mean, this is stuff that you code along the way, right?
Yeah.
It's not too, like, it's not really complicated, the interface, right? The interface is pretty simple, right? There's not that many host calls. There's only 3 entry points to a service, and maybe we might even get rid of one of them quite soon. So I don't see this as being a particularly significant roadblock. One thing that will probably kick off in parity quite soon is a very fast, high bandwidth token transfer kind of coins service. That's probably what one of our new recruits will cut his teeth on. But yeah, I think it's like time is coming to start coding services. So I invite you, play around, and initially you can keep it very simple, and I think it's still going to be very helpful. Good. Right, discussion. Any questions or topics to discuss?
Would the price and everything be extended to service implementers?
Would what be?
Or like, could the jump price or could there be later like a new incentive program for service implementers?
Not the jam prize. I don't think. Jam prize is like pretty specific for what it's for. But yeah, I mean, yeah, there could be some incentives for implementing certain services. I don't know where the incentives would necessarily come from, but I think it's kind of fun to do this, and I think there is potential benefit to the implementers in terms of sort of education and moving and you know, developing their own ability to create value using Jam. Like, there's not that much point building Jam if there are no services on it, yeah? And I think, you know, I get asked, well, what does Jam do differently? What makes it so, why should I care? And essentially it's that we're going to have an awful lot of computation and storage. Like, categorically different amount of computation and storage, and of, you know, things like continuations that allow us to do things that just conceive of things that would not otherwise have been possible in the past, using using decentralized computers, using blockchain. So it's crucial that we kind of think out of the box. Yeah, it's crucial that we don't merely try and just port stuff that's on Ethereum into Jam. That's not going to be, that's a fast way of becoming irrelevant. And so I don't know how easy it's going to be to incentivize thinking out of the box. This is not an easy thing to incentivize. Thinking out of the box comes about because someone is curious. Yeah? And I'm inviting you to be curious. And the thing is, there'll be a lot of things that you probably make that might not be that good or viable as a product. But there will inevitably, if you play around enough, be some things that actually are. And that might surprise you. I mean, you know, some stuff surprised me in crypto, or what ended up becoming a product. It's like, what the fuck is this shit? But, you know, people like it. And Jam provides a platform for creating stuff that cannot be done elsewhere, that people might like. But you're only going to get there if you are curious in the first place. Yeah, I don't believe that it's that easy to, or that outperforming well understood domains in terms of the solution that you're creating with Jam is necessarily going to give that much like economic return. Like, I think for the domains, and we can think of quite a few of them, right? So we've got like supply chain, we've got trade finance, we've got DeFi, we've got like, there's a bunch of different domains, yeah? And I think, you know, of course there'll be teams that try to use Jam in order to do those domains better and faster than others. But better and faster has not, as far as I can tell in history, been a great way of making money. Unless you're a domain insider, right? And then you can maybe swing. But then it's more about being a domain insider than about making the solution better and faster. I think what we need to think with how we need to approach things with Jam is just saying, well, we can do things that others can't. So let's play around. Let's see what we can do with this immense power that we're generating in our magic internet supercomputer. Let's assume cores are going to be really cheap. Right? I mean, if you remember in the early days of Ethereum, well, maybe not everyone does, maybe I'm one of the few that's been around for quite this time, but in the early days of Ethereum, transactions were free. Yeah, they were zero. Like, we changed the Ethereum client, parity Ethereum client, so that it could basically take the acceptable price down below the minimum to zero and allow for free transactions. Because not that many people used Ethereum, and those that did were using it because they were curious. Well, kind of have to have the same attitude with Jam, I think, if we're going to see Jam be successful. We have to kind of ignore what it is that other people are doing, ignore the tainting and the biasing of the last 10 years that have been teaching us to like think in NFTs and DeFi. We have to ignore that and say, no, actually what we have here is a internet supercomputer that's really cheap and has tons of power. And yeah, a bit of latency, but tons of power. And we have to think in those terms. We have to start thinking. Yeah. And I don't, as I said, incentivizing curiosity it's really hard. Like if you got some ideas, I'm happy to listen to them. But from my experience, it's really hard.
Hi, Gavin. What's the timeline for the service to launch?
For what, these services? I mean, it's not a launch. It's an invitation.
Yeah. So I mean, the invitation, like people can submit, like working on something. So what's the timeline?
I mean, I don't. However long. I mean, I don't know. It's it will be dependent on people having viable Jam implementations. Although that said, maybe we can give the Poker Jam testnet binary out so that people can start prototyping stuff just with that. But I mean, the timeline is now, tomorrow if you want, right? We've already developed some services. We have a Bootstrap service, right? We have some benchmarking services already in place. We have Core VM, right? It works. Yeah. It's up to people to like build on what we have, build on the thing that works. And I mean, I'm not. The story of Jam came about through an upgrade to Polkadot, right? But like Jam in principle, it's just a protocol, right? It doesn't actually have that much to do with Polkadot beyond sharing the same crypto-economic security mechanism, ELS. And the way that Jam will be utilized, quite possibly, will be very different to the Polkadot product concept, parachains, right? It's not clear to me yet that Jam will fall, just into parachains. I think there's big potential that Jam will end up being used for a lot more, maybe even the majority of Jam usage will be non-parachain usage. And if that's the case, then we should get a move on working out what this usage is, and like get a feel for how start building the SDKs and the development tools and the initial services and so on. Because at the moment we don't have them. At the moment, if you want to transfer some testnet tokens from one service to another service, you can't. You can actually. It's in the Bootstrap thing, but it's hard, right? You have to create a new Bootstrap thing every time you want to make a new account there. It's horrible. So it would be nice to start, making some crazy, some initial, silly, simple, potentially very slow, potentially very inefficient, but still kind of services that do some stuff.
Gavin, I'm curious to ask you a question. Like, is there any extra vision, like, which you would like to reach apart from decentralized network? Kind of wishful thinking or insight you would like to reach, where maybe we are just like thinking as the technology side, but maybe it's like something to come, or at least you wish that we could reach within 5 years, 10 years, I don't know, something like more beyond the technology itself?
Yeah, I'd like my own country, please. Does that count?
Well, I think so, but like I mean, regarding to the crypto, where you want that Polkadot would reach, or I don't know, crypto world would reach in general?
Where do the crypto world to reach? I don't know. I mean, I kind of grow weary of setting, 3-year, 5-year horizons for the tech, because I've been around for 11 plus years, so it's not. It never gets there. It's like, I mean, maybe it will do eventually, but it's like you have an idea about what you want to accomplish in 3 years, and you're way off. So I kind of don't really see any need to do that. But I would go outside of the tech industry. I mean, I think education is crucial. This is why I've been kind of quite a lot behind the Polkadot Blockchain Academy. And I would like to see that expanded into a permanent campus somewhere. I'm kind of, I like the idea of universities as microcosms, largely isolated from the rest of society. I think that keeps, that maximizes academic curiosity. I mean, there's a little bit of the white ivory tower syndrome, but I think it's nonetheless kind of nice to have the university be its own sort of thing. And I think this falls quite nicely in line with the broader crypto industry world, kind of. I mean, it was like this 10 years ago. It's not as much like this now, of sort of libertarianism and kind of localism and kind of trying to reduce a very opaque, semi-authoritarian government kind of overarching. So I think the two can go quite well hand in hand.
So you think more of like, let's develop the technology and see where we can achieve, or what we can achieve, where we can go, more than like, okay, I want to achieve this certain things with.
I think the technology is being developed kind of anyway, and it will get developed at its own pace. Can't develop it faster than it goes, but it will. And I think the reason I got into all of this was curiosity, and I think that's the only reason to stick around, to be honest. Everything else seems to come and go, but like curiosity is the one.
Right. Before you came here, Neil had a very nice presentation, and he was actually talking about stacks, right? The technology stacks, and let's see how technology can influence society and human behavior. And maybe what he's also referring to was maybe like we have a vision in actually how the technology, let's say on a fundamental level, will be used to change maybe how people coordinate, right, over the world. Would you like to see certain kind of applications, let's say built on top of Jam, like for example, like an email communication network or anything you would like to see actually happening?
I get asked this question so much for 11 years. No, I've given up trying to answer this question. What I want to see is what I've talked about for 11 years now. And the answer is exactly the same as it was in 2014. I want to see all of the digital public infrastructure moved to Web3.
Okay, cool. And so you want this non-permissive freedom, that anybody can actually operate and do the thing actually on the networks, independent of government.
So I mean, the vision of Jam is exactly the same as the vision that we had for Ethereum back in 2014. It's resilient public digital infrastructure. We didn't have that term for it back in 2014, but that's what it is. That's what the vision is. It's a decentralized server, and it's stuff that the world, I think, whether it wants it or not, it does need it.
Yeah,
it needs resilient. We live our lives digitally now. So what do I want to see? Well, I don't have any particular preference, right? I'm not doing this because I want to see trade finance moved onto the block. I don't care, right? What I think is important though is that the world should not crumble because all of its services, all the stuff that people need to live their lives, is run on a handful of servers that if a malicious hacker group decides to put in their spotlight, in their crosshairs, will fail, will fall over. That's not a good world to live in. Like, for the last, I don't know, basically the history of the internet, last 25 years, but 30 years, right? There's been a relative time of peace, particularly in the, in the Western world, and we've had it easy. The internet's had it easy. It's not going to have it easy much longer. Yeah. You only have to look to Sweden to see what it's like to not have it so easy. Centralized systems, right? The payments, the various payment services, which Sweden is absolutely reliant on, because they don't like to use cash there. Right? It all goes through banks. They don't even like to use government. The government doesn't run its own identity service. It just punts it off to the banks. If you want an identity in Sweden, best open a bank account. Oh, you are not allowed to? Fuck off. That's Sweden's attitude. It's a screwed attitude, but it's just a very good example of something that is emblematic everywhere. Centralized services, high barriers to entry for anyone that is not considered desirable, arbitrary decisions, and this isn't a particularly good. As I said, this is, we've had it easy. This is not a good architecture. And in the not too distant future, I suspect we will have it a lot harder still. And if we don't have these systems built and ready to go, then we're going to get screwed. And of course, whoever can sell corporates and governments highly resilient public digital infrastructure is probably going to make a bit of money out of the chaos that comes, right? So it's not to say there's no upside, you just have to be kind of missionaries, digital monks, but what do I want to see? I don't care. Right? I just don't want to see the free world crumble. That's my main design.
I think that's already a great vision. That's what I call it.
You said that with GEM, maybe we will have this digital infrastructure, but is this digital enough? Because we also have other kinds of infrastructure, as for example, we saw the energy loss that we have here in Spain and Portugal.
Yeah.
Like, there are other...
That's definitely not the Russians, by the way.
Yeah.
Definitely.
But anyway, there are other things that we need to live our lives that need to be more decentralized, not central. I don't know. I don't understand too much about energy, but I know that I felt when everything was down and people were like crazy going to supermarkets and buying waters and things like that, because it's hard to imagine the life without energy.
I mean, it's just one of a number of pieces of infrastructure that is horrendously centralized. Why? Because governments are largely inept. They buy technology from self-interested, highly centralized technology purveyors, and they've had it easy. Yeah. Energy is crazy. Energy is super centralized, and governments seem to want to centralize it ever more. It's like, no, we don't want to build any wind farms. Let's just build nuclear power plants. Okay, great, yeah. So, it takes one terrorist bombing and your entire country's energy is fucked. It's like, that is insane. Instead, we should be giving people wind turbines to stick on their roofs and solar panels to stick on their roofs and batteries to put in their walls. That's how you build a resilient society.
As even, let's say, I think even the whole European structure can go out, because all the energy systems have to be exactly in sync, exactly in harmony. So we could actually take all Europe out.
Yep. And I mean, we need better decentralized grid management, right? I mean, this Energy Web Foundation has been doing this for some years. This is sort of Ed Hesse's baby. And it's great. I mean, it's an obvious, like, no dissing to Ed, but it's like it's an obvious idea. It's like, this is obviously what we should be doing. Do the governments want to hear this? No. Right? For them, what they want to do is just partition off a bit of budget, give it to a nuclear power plant builder, get some nice fucking kickbacks, and bang, they're out. Yeah? And it's like, this isn't nation building.
And it was also in the COVID period, we also noticed it. That everything, the moment you introduce friction, like in the supply chains, like countries really get into trouble. So nothing actually is built these days or operated. It's all based on efficiency and cost, long runs, but not on. Resilience is not the thing a country thinks about, right?
No, not yet.
No.
Not yet. But yes, indeed, power is one where we have skimped on cost in order to. Skimped on cost. Skimped on resilience in order to save cost, and it's just really dumb, really dumb. And it's not the only one. Payments, the same. Telecommunications, a bit. It's not as bad, I suppose. But we should be like building mesh networks. Like this is obviously in high densely populated areas. Mesh networks are obviously the way to go.
Like radio, like or.
You know, if I walk down the street, I'll see a ton of different land, right? Well, they should just be talking to each other.
Yeah.
Packet switching, yeah? It's like, well, they don't need ISPs then. Like, they don't need many ISPs then. And if I happen to be BitTorrenting, it's going to be super, super fast, because it's going to be coming from next door. Yeah, without having to go via the ISP to their ISP, back down to them. Or if I happen to be syncing a chain, right? That's the thing. If everything is actually decentralized and your transport, your hardware transport delivery is decentralized, things work really well. And yeah, maybe maybe my phone can't join a mesh node for some reason. Maybe I'm walking in a field somewhere. That's fine. And maybe it goes to satellite. And at that point, the blockchain syncs a bit slower than it would do, or it costs a bit more, or whatever. But you know. That's called resilience. That's called graceful degradation. Yeah. This is what we should be building in.
We need to be able to launch satellites as well. Ourselves.
Well, satellites are highly centralized.
Yeah.
That's the thing, right? Don't see satellites as any kind of safe haven. They're not. And when the time comes, when a space power wants to take out some infrastructure, they will do it really easily. Right? They'll just set off an EMP in space and bam, it's gone. All your satellites, they don't work anymore. So satellites are not, like, the way to achieve resilience is through spreading your...
I'm launching my own satellite.
All right, sure. I don't know. I think this is like... quite difficult. And your satellite's still up there in space, right, ready to be taken out. Yeah. Like if your satellite happens to be the one satellite that runs like the main node of your jam instance, right? And someone wants to cause you disruption. If they are also a space power, because apparently you can launch your satellite, so guess they can as well. Then they launch a satellite with a sawn-off shotgun on it, and bam, your satellite's out of there. No, I don't. I mean, satellites are kind of. Starlink's kind of fun, but again, we've seen the issue with Starlink. It's like controlled by one mad bastard, and it's like whatever he wants. Starlink will follow. It's also not cool. But it's not resilient. I guess we're hungry.
I have one more.
Okay.
About Slipstream specifically. So our team by itself provides no security. Security comes from the development process. And only
Yeah.
thing would still be running every 6 seconds. Then what guarantees do we have about the quick, low latency block that Slipstream actually gives us?
What guarantees we have? None. Finality. We don't have any guarantees until finality, because finality only happens after auditing is finished and we are sure
What's the
whether it's
benefit
all
of
cool.
having the low latency from Slipstream?
Because some, like for Doom, you don't need to bother about waiting for the frames to be finalized before you show them. Right? It's fine. There is a degree of economic security pre-finality. Right? There is some reasonable belief that it's probably going to be fine. Because if it's not fine, someone's going to lose some money. We trust that finality will ultimately weed out the bad actors and
Not always,
slash them.
they cannot submit it to availability and then there will be no one to slash. You can't
So
wait out to availability.
indeed, so there is indeed a question as to whether you would want the service accumulation to happen after or before availability of that work item. Very important. And if you did it before, you would be, if you did accumulation before availability was guaranteed, you wouldn't have that level of security. Now this could be offset potentially by saying guarantors whose packages do not eventually make it to through assurance would be slashed in some way. It would cost them something, some small amount, right? But on the basis that it's up to them to get that package out onto the hands of other validators, and validators broadly should be benevolent. Like we expect, 2/3 of them to be benevolent, and therefore it should be fine. And then the only reason that assurance shouldn't be made is if the guarantor goes offline, or if they're scared that if they make the work package available, they'll get slashed. So we can slash them a little bit. That would be one way around. Another way is just to not do accumulations after assurance. So you've got an extra 1 second delay, potentially. Because if we have 1 second blocks, we're going to have assurance every second. I don't know. This stuff has to be, you have to model the bandwidth requirements and so on, because there'll be some things that are fixed cost, and then when you do it 6 times as often, it's going to potentially blow up some of the bandwidth. But on the face of it, it could be an interesting way to lower latency, to lower effective latency, lower practical latency. Good. All right, lunchtime. Thank you.